What is state in React? Precise definition. The shallow definition insufficient. State is data that changes in a component. True, but interviewers will push past this. The correct mental model. State is React managed, persistent, render driving data that belongs to a component or store and survives renders. So basically, it is a rendering driving data. So when you change this state, it's a data that when you change this data, it will also re-render the component, and it belongs to a component compared to a prof that belongs to a parent component that that does not belong to an individual component. Key properties that matter: owned by component or a store, just like we discussed in Redux. Persistent across renders, meaning when you render it, unless you update it, it won't change. Immutable snapshots. So there's snapshots that we will discuss later related to state that you can be changed, which allows the React to have a local state consistency. Updates, scheduled renders, asynchronous, and batch. So another thing is that it is also asynchronous, just like with Node.js. So Node.js allows you to have a single thread and concurrently execute each request from the user, while like transferring to libmove or worker threads the I/O, blocking I/O such as database calls, network calls, OS calls, etc. And all the JavaScript are executed asynchronously or concurrently. Mechanically, what actually happens when you write cons, argument parameter count comma set count equal use state argument 0 semicolon. So first stores count outside your function. So the count or this state are outside your function. Now it calls your component with current snapshot. Third, when set count is called, schedules a re-render, computes a new snapshot, re-invokes the component function. Your function does not hold the state, React does. So as you can see, the count are outside the function. That what makes the function not hold the state, because the React does, and it only it calls the component with the current snapshot, and when you update that using set count, that's the time it schedules a re-render. So this is how we update the state. So second, common errors in understanding state, errors of omission. These are dangerous later if not fixed now. Mistake number 1, thinking state is a variable. State is not a variable that changes in place. Each render sees a snapshot of state at the moment. So it doesn't actually change. It's not like when you update that, it will provide a new snapshot of state at another moment, at already updated, unlike a variable where you can change that right there. So all renders never update. Mistake number 2, thinking set states update immediately. These break asynchronous logic. So if you have set count, argument count plus 1, then console.log argument count, which is the old value. Basically, when you update a state, it doesn't update like immediately, because set state schedules work. So set state, the one that we use to update the state, doesn't immediately update the state. React controls when it runs. So it just update at, but it's still up to React with its immutable snapshot to execute the state or that request. So mistake number 3, mutating state directly. This kills React's ability to reason. So you don't actually mutate it directly, like state.value++. React depends on new reference. So you basically reference it to a new state or new snapshot instead of updating the value. Mistake number 4, confusing state ownership. If two components need the same state, it does not belong to both. It belongs to the lowest common parent. So since state is owned by component, if two components are pushing to own the state, the lowest common parent, or the lowest common parent that for that state, the lowest common parent component for that state will win. So this is directly connected to Redux or RiverPad later. So just like with RiverPad, where you instantiate a new thing instead of like having multiple updating the previous state and then updating the previous version, it makes it complicated that way. So having only one parent for that reduces the complexity. Level 2 to 4, React State Interview Q&A. So these are the exact difficulty curve you want. Level 2, Solid Junior, Early, Mid, 1 to 6 years. What's in React? State is component own data managed by React that persists across renders and trigger renders when updated. So basically, a state persists across the renders unless you update it. Therefore, it will provide React will turn to the new reference and it will trigger a new render. Second, how is state different from props? Props are external, immutable inputs controlled by the parent. So it's an input, it's still a data, but it is controlled by the parent. State is internal, owned by the component, and can be updated by the component itself. So not every component can have props. Only a parent component can have props, and a parent component could have a state, but not every child component can have a props. Basically, that's their difference. What happens when you call set state? React schedules a re-render with the new state snapshot. So with the new reference or state snapshot, the update may be batched and does not happen immediately. Why shouldn't you mutate state directly? React relies on immutability to detect changes. So providing new reference is better. Mutating state prevents React from knowing what changed. So if you mutate a directory instead of pointing to a new object reference, it will cause stale UI or bugs. So why does state survive the renders but variables don't? Because React stores state outside the function. Just like with the count earlier, we store that outside the function. So that when we update that, so that it is owned by React. At the same time, when we update, we just need to push a new reference, a new snapshot, and then push that to that function that has change variable. So because React stores state outside functions, well, variables are recreated on each function call. So in each of that function call, the variable are changed. You could think of this as rendering. So once you render a state, there's some state. You can change a variable on the front, but that state remains the same. When you should use state instead of props? Use state when the data changes over time and is owned by the component. Use props if it doesn't, like if it belongs to a parent component, not really to a child component. So we're talking to a child component here. So level 3 mid-level filter. Why is that state asynchronous? To enable batching, performance optimizations, and predictable scheduling of renders. So it allows React to control the updates and to be of course, if you batch the renders or the update, you can make a way to make it more performant, and it allows you to predict to have a predictable scheduling of all the renders, kind of like batching, because you batch it with like with your to-do list. You were able to do that because you were able to do everything at once instead of context switching. So what is a state snapshot? Each render sees a fixed, immutable snapshot of state. Updates create a new snapshot for the next render. So that, again, the state see a fixed, immutable snapshot upon each render. And an updates to that, like that with the set state, creates a new snapshot for the next render. Why can state updates be stale? Because closure capture old state snapshots when asynchronous code runs later. So if sometimes the states could be stale because it is capturing the old state snapshot. This is how you get this UI bugs in React, and that's actually how Redux are formed because they differentiate global and local state. So here, especially for asynchronous code that runs in the background, such as here, we have a Node.js and Next.js as our asynchronous code that handling process to our database request. And then at the same time, responding, going back and forth with React. So that's where the state updates can be stale. How do functional updates fix stale state? They compute the next state from the previous one. So if you have, just like with function earlier that we update to fix that stale state, we compute the next state from the previous one. So here's that count argument pref arrow2 pref plus 1. So implementing this in your function avoids that fixed state stale. So this is one of the best code practices when writing the state code in your React. So when should state be lifted up? When multiple components need to read or update the same state. So you would lift up the state. For example, some component um, have the state in that render. So when multiple components need to read or update that state, that's the time you would lift it up because a lot of requesting of it already. And therefore that state better be on those state request or component that request the lowest common parent that requests it. So why is derived state an anti-pattern? It duplicates source of truth, leading to inconsistencies and bug. So if you derive a state, basically it vanish React's one source of truth. It doesn't really go to a new reference. So if you derive a state, kind of like update it, it really remove the single source of truth or the single source of control of React that leads to inconsistencies in bugs. Kind of like with Redux, the reason why Redux provide a new version is because it avoids you from having those tail updates with the previous version. So how does React know a state update happened? By comparing object references, not diff values. So it doesn't check the values, it check the object references. So that's how it also do the snapshot. That's how it provides the new snapshot when the state update. So what happens if you set the same state value again? React may bail out and skip re-rendering if the reference hasn't changed. So just because this is what makes React consistent as well upon renders is when you update or when you set the same state value again, React won't re-render because it has the same object reference as before. So basically, it's just the same snapshot. The only way is to change the value of the state or to change the data for it to re-render and produce a new object reference. So explain state updates in concurrent rendering. State updates may be interrupted, reordered, or discarded. React ensures consistency by working with immutable snapshots. So again, since it is requesting to the server, that could have a network interruption. It could be reordered, the packets could be reordered or be discarded by the server. That's where the retry comes, right? So React ensures the consistency by working with immutable snapshots. So because you can mutate the snapshots, you can only reference to a new, you can only have new reference when updating. That's where the React are able to maintain or get into with the concurrent rendering from the server or the Node.js. So wire a state updates batch to minimize a render and improve performance. So not just re-renders, it's also performance. So how does states relate to React's render and commit phrases? State updates trigger render, pure computation, and commit the mutation. So a state is related to render. By updating it, it triggers a render, a pure computation. And the state is related to commit phases via DOM mutation. So when you commit something in front end, you really change the DOM or mutate it. So what problems arise from overusing local state? Duplication, prop drilling. So local state is that when you use this state locally instead of globally, when you implement a state very specialized, let's say you have like grandchildren and that grandchildren owns that state, you risk the prop drilling, which is when a parent passed a state or a props to let's see. So when a parent or props passing a data which is props to the component and its intermediate children and then grandchildren that is not really that grandchildren, so that's where the prop drilling comes. So that's what you do when you overuse local state. That's the reason why you should avoid local state as much as possible. You should do not overuse it, especially for deep components. Duplication, so you could also duplicate those data, which provides inconsistency and bugs. Of course, synchronization bugs. It won't be synchronized. So because it has duplicate data or some components are not have data, some intermediate components have data that's not for them. You have this synchronization across devices issues and poor scalability. Because how would you scale an inconsistent data? So state triggers the renders. Refs, how does state differ from refs? State triggers renders. Refs persist values without causing the renders. So it has a value. So when you change its value, unlike with state, it doesn't render the state, or it React doesn't really provide or schedule a new re-render or change a new object reference. You just change the value on that thing or that component without re-rendering. When would you move state out of React entirely? When state must persist across routes, sessions, or shared globally. So this is where the routes of Redux, the session, the shared global. So how this ties to your previous conversation during SOFA Redux or Riverpad Global State, Atomic DB updates consistency, event loop scheduling, props, immutable input state, own mutable snapshot, they all follow the same rule. Immutable inputs plus scheduled updates plus centralized ownership. This is the same pattern as the state, Redux, Riverpad, database, payment retries. So for database, we have consistency. For Redux, that means global state. For event loop, that scheduling. For props, that's the immutable data. So that's for React. For state, for React is own mutable snapshots. So basically, that's owned by computed component and it's mutable snapshot, meaning you have immutable snapshot across each render. So as you can see, across the stocks from Redux to database to event loop scheduling, which provides concurrency. It allows us to manage multiple data at once. So they all follow the same rule. Immutable inputs, you cannot change what you already input. Scheduled updates, like the scheduler of event loops, and centralized ownership, which is the Redux, and the React and parent prof as well. So this is the same pattern: React states, Redux, Riverpod database, payment retries. So it's across all stuff. You're not learning random topics, you're learning one mental model across systems. Let's see the other questions here. So what is back pressure and why does it matter in Node.js? I think we're not there yet. Sorry. Oh. Yeah, I think we're here. So what is back pressure and why does it matter in Node.js? Back pressure is the mechanism that prevents a fast producer from overwhelming a slow consumer. So let's say you have like a fast producer from the server. It won't you want to avoid overwhelming the consumer or the front end, which is React and Next.js. In Node Stream support back pressure natively. So this stream, kind of like you will just import that in your Node code. It would support that feature. Without it, memory usage spikes and system crash under load. So basically, if you have this server that has a lot of power to provide to the client, and the client is not ready to absorb it, therefore you're gonna have a lot of resource. You'll not be able to utilize a lot of your resource, and you get a lot of memory spikes because you have a lot of this fast producer that doesn't really help or doesn't really synchronize with the front end, and the system crash under load. So when the load really has executed from the front end, and all of that resource has been technically used, therefore it could cause a system crash. So how does Node.js handles I/O differently from CPU bound task? I/O is handled asynchronously via the event loop and OS facilities, while CPU bound tasks block the event loop and must be offloaded to worker threads or separate processes. So this is where a normal JavaScript, an I/O, and a CPU-bound task or executions in Node.js are different. For I/O, it is handled asynchronously via the event loop and OS facilities, which is the libov library. While for CPU-bound tasks like block the event loop, so a CPU-bound task really can't be inside the event loop or with I/O and the JavaScript code at the same time, because it must be offloaded to worker threads or separate process that handle that, because it will block the event loop. Therefore, you won't be able to provide asynchronous, and therefore you will have a slow server. So why blocking event loop dangerous even for short task? Because it blocks all other requests from the client. So let's say you're serving like 30,000 users. Even a short block of that, even a 50 milliseconds block multiplied by traffic causes cascading latency and timeouts. So imagine that 50 milliseconds block across your 100,000 users, and it will block, all of them request multiple times at the same time. You get a lot of like those compounds, especially for the long wait in queue or the last one we request. It may take like an hour for them to respond. So those are not acceptable in financial application. What is Libov and why does Node depend on it? Libov is a C library that abstracts OS level asynchronous I/O and provides the event loop, thread pool, and cross-platform consistency. So it is the one that provides the asynchronous operation. That's what made Node.js just pass those asynchronous I/O while doing other JavaScript stuff in the backend. Um, mm, so it's a C library that abstracts that OS level asynchronous because OS, of course, contacts the database, which is that's how you do I/O depending on your system architectures. This C library works across stacks across OSs such as Linux OS, so it provides a cross-platform concurrency. Yeah, so that's what makes your thread event loop works. Node.js is essentially JavaScript on top of liboof or C library. So what goes into the liboof thread pool? File system operations. So not just an I/O. So this is this is the details of I/O. It does a file system operations, writing, deleting, updating, a DNS lookup. So let's say your request from the client React or requesting kind of like requesting your site, a crypto. So let's say you have a cryptographic secure communication or API outside that would encapsulate that request. A compression, so let's say you would compress that before like a writing. Let's say the overall application provides like compression features which allows you to store a lot of request data, which you will be then doing analytics later. So tasks that can be done asynchronously by the OS. So if you're just relying on OS without that library, you won't be able to do an asynchronous task on that because the OS code are limited in running the Node.js event loop alone. So those tasks, if you have a library or specialized task that handles those operations, you would be able to handle it better. So what happens if the liboof thread pool is saturated? So if the thread pool is saturated, kind of like with the event loop or saturated, task queue up, latency spikes, and unrelated operations like file read slow down. This is a common hidden bottleneck. So not just event loop that actually became saturated, we also need to concern yourself with the liboof C library. So how does Node achieve concurrency without parallelism? By interleaving tasks using the event loop, multiple operations make progress, but only one JavaScript frame executes at a time. When does Node actually become parallel? When using worker threads, clustering, or native modules. So let's say you have like a CPU bound task. The financial that has less CPU and more of an IO. So let's say you have a CPU bound task and it's really a lot in your app. You pass that in worker threads and your worker threads would run that CPU task in parallel because it working directly with the CPU, kind of like with the one discussed with the database, with the compressed database for analytics, something like that. It's near on the CPU or native modules that execute outside the main JS thread. So when you have a specialized modules as well, aside from the CPU, it could actually provide that parallelism because it's specialized. So explain the difference between process.next tick, promises, and set time immediate. Answer: next tick runs before the event loop continues. Promises run in the microtask queue. Set immediate runs in the check phase. Misusing this can starve the event loop. So as you can see, we have like beginning, middle, and end. The next tick runs before the event loop continues. So that's the first one that runs before the event loop could process another request or continue. It will run next tick and then promises run in the micro task queue. So while executing, you will run these promises because that's the promise that you would execute that later for that request. Now set immediate runs in check phase at the end. So misusing this, using a set immediate at the beginning or next tick at the check phase or at the end, or promises at the beginning or set immediate at the micro task or while other are executing, can starve the event loop and therefore leads to bottleneck. How would you detect event loop blocking in production? By measuring event loop log, request latency, and CPU usage. So tools like Clinic.js or built-in performance hooks helps. So the way to fix this performance problem is really to use Clinic.js or a third-party library which has a built-in performance hooks. So what you're measuring here is a request latency. How would you respond to request over time, and the CPU usage of those requests? Because if you have a lot of like CPU usage, that's a bad indicator. Or if you have a huge latency and to your request, because those are measured as well, how long you respond to the customer, and by measuring event loop log. So an event loop log, basically, you have log in executing those asynchronously, the JavaScript code. Let's say some of that are executed, the first 5 are executed fast enough, but the next 5 are not. So why are queues common in payment system? They decouple request handling from processing, absorb traffic spikes, and allow retries and failure isolation. So queues are common across the whole system, across each stack from request handling, processing, from absorbing traffic spikes. So when you have a lot of requests, you wouldn't want that last request to ignore. You want them to wait. So that's where the queue came. And that's also how you allow the retries and failure isolation. So a retries, basically when you have this request that didn't go through and therefore have to retry, that's also where queue comes, because like for example that there's a queue and it is the last thing, you know, you wouldn't want to reject them. You want them to retry because others requests will be finished out later. And a failure isolation as well, because this remember, like we need to one of the hardest part with idempotency is that distinguishing each request about their failure reason. You're not just handling each request at the same way. You're handling them differently. So queue is one of the information that will allow us to learn like boost first and boost last request, and how long. So queue will help us determine how long that request have been and how many times did it retry. So that's you know, that's why queues are common in payment systems. So what guarantees does a queue provide that HTTP does not? Durability, ordering, sometimes retries, and back pressure. So a queue are inherently supported with the back pressure that inherently supported by Node.js we discussed earlier, and a durability because you make sure that each request goes through the server regardless of how long it is. Ordering as well, you make sure that the first request comes first. So that's the guarantee the queue provides to that the HTTP does not. How do you ensure exactly one processing in this? How do you ensure exactly one's processing in the distributed systems? You don't practically, you design for at least once delivery with idempotent consumers. So you don't actually ensure just one processing. You design for at least once delivery with idempotent consumers, meaning the user could request once or it could request twice, and you handle this the same way based on their intent and context. So what is a saga pattern? A sequence of local transactions coordinated via events with compensating actions instead of global locks. So a saga pattern is a sequence of a local coordinated transactions that you coordinate via events with compensating actions. So basically, there is a consequences for that, and I mean all of that local sequence transaction affects itself instead of like a global locks. So you don't like kind of maintain a global locks because those sequence of transactions don't really have those locks in it. Why are distributed transactions avoided? They are slow, fragile, and don't scale well across services. So how would you version APIs without breaking clients? Additive changes, feature flags, backdoor compatible defaults. So this is the key is that you make sure that the version of the code or logic you're implementing are backward compatible to their defaults to be able to adapt to change easily. So that's how you version the API. You basically improve it with thinking that you can easily backward it later. That's how you also prevent like those how you fix those midnight issues and explicit versioning when necessary. So explicit, basically you make it clear that you would version it. And additive changes, so instead of updating, you change it. Same principle with Redux. You add the change and then produce a new version. A feature flags, meaning you would so a feature flags, this is what we discussed with a previous thing with Redux. You basically allows or prepare, allows this feature to be toggled on and off whenever necessary. So this allows you to be able to disable this if this feature are causing an issue. So what's the difference between throughput and latency? Throughput is how much work is done. Latency is how long each request takes. So a throughput is with the Node.js, because it can handle a lot of work or a lot of requests concurrently. Therefore, it has a high throughput. So if it's sequential and not concurrent, it would not have a high throughput. For latency is how long each request takes, because again, you execute those requests each in the event loop, and each request has different time frame on how it will finish. So that's latency. So that latency, since each requests are being measured, it also related to the I/O or the libov. So if the thread full of libov also were blocked, it will affect the latency. However, the throughput, I mean, yeah, it is affected by it, but it's more of a number of requests than individual request measurement. So optimizing one can hurt the other. So as you can see, they are connected because they're in the same loop. How does caching break systems? Stale data, cache stampedes, invalidation bugs. So when you invalidate something, you thought you invalidate, but it's the same thing, and inconsistent state across nodes. That's the downside of caching. That's why we also have the stateless server, where it doesn't really remember or doesn't really kind of cache it, but you have to provide the information needed in each request rather than persisting that information in a session. As stale data, so that's also an issue with React or the front end, not just the back end. So like, for example, in my LiveKit app, I have like this different version of the app for different profile. So that's the downside of caching. What makes fintech systems harder than typical crude apps? Regulatory constraints. Correctness is greater than speed, auditability, traceability, and irreversible consequences. What would you ask if you joined the company? How do we reason about failure, retries, and correctness today? And where do we still rely on assumptions? Deep dive, Node.js event loop and concurrency, no hand waving. Let's rebuild your mental model from the ground up cleanly. The common but incomplete mental model you probably have. Node is a single-threaded async, non-blocking, uses an event loop. This is true but dangerously shallow. The correct mental model, Node.js is single-threaded for JavaScript execution, multi-threaded underneath, event-driven, not parallel by default, concurrency via interleaving, not simultaneous execution. The event loop, precisely, the event loop is a state machine that repeatedly runs phases. First, timers, set timeout, set interval. Second, IO callbacks. Third, idle or prepare. Fourth, poll, most IO waits here. Fifth, check, set immediate. Sixth, close callbacks. So between every phase, we have microtask run, promises. Every process the next ticks runs even earlier. Critical precision you may be missing. Error of omission number 1. Async means parallel, false. Async means the thread is not blocked while waiting. It does not mean multiple JS tasks run at the same time. Error of omission number 2. Node handles everything asynchronously, false. Some operations, file IO, crypto, DNS are actually offloaded to a threaded pool, not truly async. Error of omission number 3. Promises are just nicer callbacks. Dangerous. Promises run in the microtask queue can starve the event loop, have a higher priority than timers. Infinite promise chains equal production outage. So if you have an infinite a lot of promises, it will outage your production because that has higher priority than timers. Subtle misunderstanding that will hurt you later. Thinking the event loop is magic, it's not, it's deterministic. You can predict execution order correctly. If you can't, you don't fully understand Node yet. Underestimating microtasks. Microtasks can block timers and I/O. This matters in high throughput APIs, payment retries, real-time systems. Confusing concurrency with scalability. Node handles many connections well. It does not handle heavy computation well. Scaling Node is not equal throwing more async at it. Ignoring event log. Event loop log. Event loop log is a system health metric, not trivia. If you don't measure it, you don't know when you're dying. Assuming retries are harmless, retries plus async systems is equal retime storms. This connects directly to smart retry business problem. When you're understanding still hand wavy, be honest, you likely can explain what async is, but not where code execute or what queue it lands in or why timing bug happens. That's okay, but now you know what to sharpen. What you should be able to do next, this is the goal. Predict execution order of async code, explain why a node server hangs, decide when to use workers versus queues, reason about retries plus idempotency plus event loop pressure.